Last time we looked at the Laplace transform. This time we will look at the inverse transform. So L of f of t is going to equal big F of s. We say that f of t is an inverse Laplace transform of big F of s. And it's written f of t equals L to the minus 1 of big F of s. Some basic inverse transforms follow directly from the basic transforms we studied last time. So the inverse transform of 1 over s is 1. The inverse transform of n factorial over s to the n plus 1 is t to the n, where n is a positive integer. The inverse transform of 1 over s minus n is 1 over s minus a is e to the at. The inverse transform of k over s squared plus k squared is sine of kt. The inverse transform of s over s squared plus k squared is cosine of kt. The inverse transform of s over s squared minus k squared is the hyperbolic sine of kt. And the inverse transform of k over s squared minus k squared is the hyperbolic cosine of kt. So we're going to use these to calculate some inverse Laplace transforms. So let's take a look at the inverse transform of 1 over s to the 5th power. Well, we have to rewrite this. We can put a 4 factorial in the numerator as long as we put a 4 factorial in the denominator. Four factorial is 24, so we can factor out a 1 over 24. And we're going to be left with 4 factorial over s to the 5th power. And that is t, or I'm sorry, rewrite it as 1 over 24 inverse transform 4 factorial over s to the 4 plus 1, just to force it to fit the form. 4 factorial, inverse transform of 4 factorial over s to the 4 plus 1 is t to the 4th power. So this transform is t to the 4th over 24. Let's look at the inverse transform of 1 over s squared plus 7. So this will be the inverse transform of the square root of 7 over square root of 7 times s squared plus 7. Sorry, we can factor out 1 over root 7. We're left with the inverse transform of root 7 over s squared plus root 7 squared. So this is 1 over root 7 sine of the square root of 7t. So now we're going to look at the inverse transform of s squared plus 6s plus 9 over s minus 1 times s minus 2 times s plus 4. Now this one we're going to have to actually do a little bit more algebra on. So let's go ahead and look at s squared plus 6s plus 9 over s minus 1 times s minus 2 times s plus 4. We're going to use partial fraction decomposition on this. So now multiply by the least common denominator. So I have a times s minus 2 times s plus 4 plus b times s minus 1 times s plus 4 plus c times s minus 2 times s minus 1. By using s equals 1, s equals 2, and s equals negative 4 respectively, we'll find that a is negative 16 over 5, b is 25 over 6, and c is 1/30. So our Laplace transform can now be written as negative 16 over 5 inverse transform of 1 over s minus 1 plus 25 over 6 inverse transform of 1 over s minus 2 plus 1/30 inverse transform of 1 over s plus 4. So we get negative 16/5 e to the t plus 25 over 6 e to the 2t plus 1/30 e to the negative 4t as our inverse transform. Now, if f prime is continuous for t greater than or equal to 0, if we take the Laplace transform of f of t, we'll get the integral from 0 to infinity e to the negative s of t times f prime of t dt, which integration by parts will give us e to the negative s of t times f of t divided from t equals 0 to infinity minus, or rather plus, s times the integral from 0 to infinity of e to the negative s of t times f of t dt. If we look at this first part, as t goes to infinity, this will go to 0, so we're left with f of 0, negative f of 0, minus, now this integral is the Laplace transform, so it's s Laplace transform of f of t. And that should be plus, not minus. So we get s times big F of s minus f of 0. If we now look at the Laplace transform of f double prime of t, it's going to follow a similar format. So we have integral e to the negative s of t f double prime of t dt. So integration by parts, we'll get e to the negative s of t times f prime of t from t equals 0 to infinity, plus s times the integral from 0 to infinity, e to the negative st times f prime of t dt. This will give us negative negative f prime of 0. Now this we just calculated. So plus s f of s minus f of 0, and I'm sorry, s squared. Now let me do it this way. S times s f of s minus f of 0. And so we get s squared f of s minus s f of 0 minus f prime of 0. In general, we have f prime all the way up to the n minus first derivative as continuous on 0 to infinity and are of exponential order. And if the nth derivative is piecewise continuous, on the same interval 0 to infinity, then the Laplace transform of the nth derivative of f will be s to the n f of s minus s to the n minus 1 f of 0 minus s to the n minus 2 f prime of 0 minus so on and so forth till we get to n minus first derivative of f. Evaluate 0, we'll remember big F of s is the Laplace transform of f of t. This is important because this is going to allow us to use the Laplace transforms to solve initial value problems. So let's look at the linear differential equation, or initial value problem rather. A sub n, nth derivative of y, plus a sub n minus 1, n minus 1 derivative of y, so on and so forth. A sub 1 y prime plus a naught y is equal to g of x, with the conditions that y of 0 is equal to y naught, y prime of 0 is equal to y1, the n minus 1 derivative of 0 is y sub n minus 1. Now, each of the ai's are constant, each of the yi's are constant. We can take the Laplace transform of both sides, and using linearity, we will wind up with a sub n, Laplace transform of the nth derivative of y, plus a sub n minus 1 times Laplace transform of the n minus 1 derivative of y, yada yada yada, plus a1 Laplace transform of y prime, plus a naught Laplace transform of y, is equal to the Laplace transform of g of x. This will become, from our previous discussion, a sub n times Sn big Y of s minus s to the n minus 1, y of 0 minus yada yada yada, minus n minus 1 derivative of y of 0 plus a n minus 1 times s to the n minus 1 big Y of s minus s to the n minus 2 y of 0, so on and so forth, and we'll have n minus 2 derivative of y evaluated at 0. This keeps going until we finally have a naught times big Y of s is equal to big G of s. Now notice that this is an algebraic equation in terms of big Y of s. So we will algebraically solve for big Y of s. Then take the inverse transform. This will give us a solution of the form y of t is equal to the inverse transform of big Y of s. Sorry, y of x. So let's look at a real simple second order initial value problem. Y double prime plus 6y prime plus 5y is equal to 3e to the negative 2t. Given the conditions, y of 0 is equal to 1 and y prime of 0 is equal to negative 1. Now before I start, I recommend that you pause this video and try to solve this using the methods we discussed earlier, specifically undetermined coefficients. When you have your solution, then come back to this video and follow along with the method I'm about to do. So, take the Laplace transforms of both sides, so we get Laplace transform of y double prime plus 6y prime plus 5y is equal to the Laplace transform of 3e to the negative 2t. This will give Laplace transform of y double prime plus 6 times Laplace transform of y prime plus 5 times Laplace transform of y is equal to 3 times Laplace transform of e to the negative 2t. Which becomes s squared times y of s minus s y of 0 minus y prime of 0. So that's just Laplace transform of y double prime plus 6 times s y of s minus minus y of 0 plus 5 times y of s is equal to 3 over s plus 2. Y of 0 was 1, y prime of 0 is minus 1, so plug those values in. We'll have s squared times y of s minus s times 1 minus negative 1 plus 6s y of s minus 6 plus 5 times y of s is equal to 3 over s plus 2. Group together all our y of s terms. S squared plus 6s plus 5 times y of s. I'm going to move all the other terms over, so we get is equal to 3 over s plus 2 plus s minus 1 plus 6, which is 3 over s plus 2 plus s plus 5. Let's go ahead and write that as a single fraction. So we're going to have 3 plus s times s plus 2 plus 5 times s plus 2 all over s plus 2. Alright, so simplifying, we'll have s squared, 2s right, 2 times s, 5 times s, so plus 7s, 10 and 3 plus 13 all over s plus 2. Now we can go ahead and solve for y of s. So it is s squared plus 7s plus 13 all over s plus 2 times s squared plus 6s plus 5. We want to fully factor the denominator. So we get s plus 2 times s plus 1 times s plus 5. So we now want to work with this. We want to use partial fraction decomposition. We want it with s squared plus 7s plus 13 is equal to a times s plus 1, s plus 5, plus b times s plus 2 times s plus 5, plus c times s plus 2 times s plus 1. Solve for this. You'll find that a is -1, b is 7/4, and c is 1/4. So y of s is equal to 7/4 times 1 over s plus 1 plus 1/4 times 1 over s plus 5 minus 1 over s plus 2. So our solution y of t is the inverse of y of s. So we get 7/4 times the inverse transform of 1 over s plus 1 plus 1/4 times the inverse transform of 1 over s plus 5 minus the inverse transform of 1 over s plus 2. So y of t is 7/4 e to the negative t plus 1/4 e to the negative 5t minus e to the negative 2t. That concludes this lesson. I hope you've learned something. and we will see you in the next one.